On November the 1st, 1983, Moscow and Washington were linked by satellite and television for a most unusual scientific conference.
Я бы хотел предоставить слово Юрию Антоновичу Израилю. Пожалуйста. Благодарю вас.
Leading scientists from East and West had gathered to discuss the consequences to our planet of a nuclear war, using simultaneous translation.
Circumstances of an increasing arms race has already led to the appearance of a number of global ecological problems. It is quite clear that in the event of a nuclear war, the effect on the biosphere will be magnified many times.
The conference was called by independent American scientists, including Carl Sagan, the astronomer, on the left, and Paul Ehrlich, biologist. Their purpose was to discuss new work by atmospheric scientists, which predicts that the climate of the Earth could change dramatically after a nuclear war, with weeks or months of darkness and intense cold.
It was no surprise to my colleagues in the Soviet Union, namely that a very large group of prominent biologists in the United States presented with the scenarios that Dr. Sagan just described could come to a unanimous conclusion on the consequences for biological systems.
The drop in temperature being discussed would be great enough to cause the extinction of thousands of species and to destroy food crops over much of the planet. Results that cast doubt on the credibility of current nuclear strategy.
In a so-called limited nuclear war. This again stresses that in a nuclear war there can be no victor and no vanquished. In the final analysis, all sides suffer fatally, and Professor Sagan has already spoken of this at the beginning of the conference. Thus we are raising the very question of life on Earth.
The nuclear age began when the first atom bomb was exploded in 1945 in New Mexico. Scientists then knew little about the effects of a nuclear explosion. But now it's thought that this test may have caused hundreds of deaths from leukemia. Only 3 weeks later, the first atom bomb was used in warfare. Hiroshima had been spared conventional bombing so that the effects of this grim experiment could be documented with precision. Time stood still at 12 minutes past 8 on August the 6th. 6 months later, a Hollywood film crew was conscripted to record the devastation. What the film cannot show is that more than a third of the energy of the bomb was released as heat. In 1980, witnesses of the attack gave evidence to a Senate committee in Washington.
That morning I heard the airplane, and I looked up and I saw something drop from the plane. And just then I felt a strong wind and strong light, and I was knocked down. Suddenly, I was sort of in a big fire, red, grey, dark. I could not see anything. Then, I cannot say how long it took, and I could see around. Surrounding me was like a different world, completely changed, sort of a hell. The people were not like people, more like monsters. I'd never seen such a horrible-looking people.
I was thrown across the schoolyard. The air was so hot I thought I would die. And the next thing I knew, we were right in the middle of a black, tarry rain. That was the radioactive rain that came down. And I recall very clearly people dead, just standing. And you would think they were still alive standing there. And they are just completely charred. People on bicycles in an upright position, frozen and dead.
My first impression was of darkness. I suppose it was all the ashes that were thrown up in the air. As it cleared up, you could see people in waves coming, and they were burned. You could not tell which was their face or which part their back. It seemed they were in a daze. Most of them were stunned, many were crying. Mothers carrying their half-burned children. The mothers themselves were burned, more than half of their bodies. Skin hanging from the child, skin hanging from their own bodies, practically to the ground.
Scientists have now had 39 years to quantify the effects of the two bombs dropped on Hiroshima and Nagasaki. Effects so overwhelming in scale that although both official and independent publications now write of nuclear war, military thinking is still dominated by the effects of single weapons. Weapons of ever-increasing ingenuity and accuracy. The standard nuclear warfare textbook, published by the American Department of Defense, comes complete with a handy plastic computer. You can dial the warhead yield to give the optimum outcome. Many tests of fireball and blast wave from small single warheads were carried out on military equipment in Nevada and the Soviet Union. "450 nuclear warheads were exploded in the atmosphere before the Test Ban Treaty was signed in 1963.
But often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on Shot 9. A study of tactical importance. 145 ponderosa pines set in concrete.
To the military, a forest is only a place where you hide troops or shelter them from attack. So they cut down pine trees, then planted them in concrete in the desert to measure what happened.
Anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Static pressures around 4 psi. Post-blast survey indicated that
This is not the way to find out what a nuclear blast does to a living forest. American and British tests were in deserts or on Pacific islands, where it was impossible to measure their effects on the fragile living ecosystems that support life on this planet. Here at Brookhaven, New York, a forest was subjected to gamma rays similar to those that occur with a nuclear explosion. The radiation from a small source on a tower destroyed all vegetation at the center. Further away, as it became less intense, the more resistant plants could survive. The hardiest plants were grass and sedges, and some species of lichens. It was also discovered some populations of insect pests increased. Pine trees were killed more easily than oak, but the steady radiation used here was very different from the beta and gamma doses that come from fallout. Meanwhile, in 1952, America had exploded the first H-bomb, 1,000 times more powerful than the atom bombs. More and more power was added to the nuclear arsenals. There have now been over 1,400 warheads tested. All the death and devastation of World War II was caused by the equivalent of 3 million tons of high explosive, 3 megatons. If we represent all that power by one symbol, this is the equivalent power of the world nuclear arsenal now. $18,000 million tons, more than 1 million Hiroshimas. Less than 1% of this explosive power would be enough to destroy every large and medium-sized city in the world. This is what just 1 ton of high explosive can do. This was an 8-story building, the headquarters of the US Marines in Lebanon. 1 ton of explosive reduced it to rubble and killed 241 people. We have now stored in the nuclear arsenal the power of more than 4 tons of explosive for every man, woman and child on the planet. How did this happen? In 1945, there were just 2 nuclear bombs used by America against Japan. By 1952, America had 1,000 bombs and Russia probably had about 6. The nuclear arms race had begun. In the late 1960s, America scrapped some of its earlier obsolete bombs and the total went down, for a while. Britain probably now has about 1,000 warheads. France and China, roughly the same total each. There are now about 54,000 nuclear warheads. Modern missiles are more accurate, so the warheads are smaller, but the numbers are going up again. 10 new warheads are made every day. How are such enormous numbers targeted? Modern nuclear war strategy is to aim warheads first at priority targets, missile silos, and missile-carrying submarine bases. Then the vital communications, radar and intelligence centers. Then major airfields and naval bases. It's generally accepted by military analysts that once a nuclear war starts, it will inevitably become a major exchange. To the layman, it would seem obvious that the explosion of some 5 or more billion tons of weapon power would seriously damage the planet. But until 1982, all published scientific work maintained the opposite. The first clue that this might be an appalling error came completely by accident, and ironically, by looking at a different planet altogether. In November 1971, a spacecraft was launched. It was Mariner 9, the first to orbit another planet. As it approached Mars, astronomers eagerly awaited their first close-up look at the red planet. Suddenly, to their dismay, a huge global dust storm completely hid its features. One of the research teams studying Mars was Carl Sagan of Cornell University, New York.
There was an instrument on board the spacecraft which was able to measure the temperature at various levels in the Martian atmosphere and down to the surface despite the dust cover. And what the instrument showed was that the upper atmosphere was much warmer than was usual for Mars, and the surface was much colder than was usual for Mars. And qualitatively, the reason is very clear. The fine dust absorbs sunlight high up and heats the surrounding air. Because the fine dust absorbs the sunlight can't get down to the surface as much as it ordinarily does, and so the surface was cooler and darker.
It was another 5 years before Viking 2 actually landed on Mars and radioed back photographs showing the drifts of fine dust that had caused the trouble. In the meantime, the astronomers looked for ways to apply their new knowledge. One of Sagan's colleagues, now working at NASA in California, is Brian Toon.
When we did these studies to understand how the dust had changed the atmosphere of Mars, it occurred to us that a similar thing happened on the Earth. Gigantic volcanoes went off, put massive amounts of material into the atmosphere of the Earth, and perhaps changed the climate. So there is an interesting parallel between Mars and the Earth. Now, even though Martian dust storms occur every year, so that one has simple and obvious observations of these things, gigantic volcanoes don't erupt very frequently, fortunately, on the Earth. And there, in fact, has only been one in the last century. So the only way for us to really understand how these volcanoes affect climate was to try to make models to predict what the clouds from the volcanoes were like, so that given the lack of observations, we could make a computer model to provide us with computer observations.
Then, again by chance, in May 1980, Mount St. Helens erupted, only 600 miles away in Oregon. The eruptions threw 1/4 of a cubic mile of dust and ash high into the atmosphere. Downwind, the effect was dramatic. This is midday in the town of Yakima. The sunlight has been completely cut off by the falling ash. The people of Yakima thought it was the end of the world, but the effect was only local. In April 1982, another volcano, El Chichon, blew up in the remote Chiapas province of Mexico. 200 lives were lost in the village of San Francisco Leon, overwhelmed by the eruption at dawn on Palm Sunday. Plumes of dust from the eruptions could be seen clearly on infrared satellite photographs. The dust circled the globe in 3 weeks. And it was no ordinary cloud.
The cloud contains about 10 million tons of sulfuric acid, so concentrated that if you got it on your hands, you'd be badly burned. And the effects of this cloud on the sunlight, which is trying to pass through the cloud and get to the surface where it can warm us, those effects are very dramatic and obvious to everyone. In the sunsets that we've seen between 1982 and on into 1984, beautiful purple and violet colors have been seen, and these are due to the volcanic particles. There's also a large whitish area that's very bright around the sun, and that's due also to these volcanic particles scattering the sunlight out into the sky. Now, when these particles scatter the sunlight, they scatter a lot out into the sky, but they also scatter some back to space. That means less sunlight gets to the Earth's surface. And when less sunlight gets to the Earth's surface, it loses energy and begins to cool off. Now, the effects of the volcano on the Earth's surface are small. They're hardly bigger than the random year-to-year fluctuations in our climate. That makes it very difficult for us to reliably detect them. But nevertheless, there are good reasons for believing that this volcanic cloud has played an important role in causing the climatic anomalies of 1982 and 1983, some of which have been century extremes in weather.
Mount St. Helens had thrown ash to the height at which passenger jets fly, below the top of the weather layer, which is reached by the summit of the highest thunderclouds. So rain could wash out the ash fairly quickly, and it had no lasting effect on the climate. Above this troposphere is the stratosphere, a region where the air is thin, cold, and stable. The cloud of sulfates from El Chichon erupted with more force. It rose high into the stratosphere, where it will remain for years, scattering the energy of the sun. But there have been far more dramatic dust clouds. One may have killed off the dinosaurs. There is compelling evidence that they were made extinct by a meteorite hitting the Earth.
Well, in 1980, a group of scientists at Berkeley, led by Walter and Louis Alvarez, discovered that the Earth was covered by a layer of meteoritic material about 1 centimeter thick. And this meteoritic material is found in rocks about 65 million years ago, marking a position below which dinosaurs and other creatures of long ago eras existed, and above which they had all vanished. So it appeared experimentally that this meteoritic layer was the cause somehow of the extinction of more than 50% of all of the species on the planet. It was a mammoth catastrophe attached to this meteoritic impact. Well, the evidence that was found for the meteorite didn't explain how it could be that the meteorite would have led to the extinctions. So our interest was, what effects would a large amount of meteoritic dust spread globally in the atmosphere have? Would it block out the sun or not? Would it cause the Earth to warm up or to cool off? We found to our surprise that the effects were very dramatic. Not only was light totally blocked off from the surface for a period of 3 or 4 months, but the surface temperatures over the continental regions plummeted rapidly below freezing. So we had a condition where over the continents there was no light to see and temperatures were below freezing.
During those months of darkness, plants would have died, animals starved. As recently as 1975, the American National Academy of Sciences published a report maintaining that there would be little atmospheric effect from dust after a nuclear war. It was only by chance that Brian Toon was drawn to examine this question.
During our dinosaur work, I happened to attend a meeting in which I presented the results of our studies of what the big meteoritic cloud might have done to the Earth's climate. And at that meeting, there were several people who happened to be interested themselves in the nuclear war issue. And they asked me and my colleagues who had studied the dinosaur problem to think about what nuclear wars might be like and how they might be related to the dinosaur problem. So in response to that, we did begin to think about this question. And much to our surprise, we discovered that even considering only the dust that was lifted by surface explosions of nuclear weapons, that very significant amounts of dust might be lifted into the atmosphere. And the critical ingredient, I think, that we had that allowed us to make some progress in this area was a model that could calculate what the physics of such clouds of dust might be. Previous to our studies of volcanic explosions, no one had such a model. So it was not until the time that this model was developed that one could really quantify the density of the nuclear clouds that might develop after a large-scale war.
It was the Royal Academy of Sciences of a neutral country, Sweden, that commissioned the next crucial scientific report. This review by leading scientists in many fields was published in 1982. Two atmospheric chemists were asked to calculate whether nuclear explosions would produce ozone in the troposphere. Director of the Max Planck Institute for Chemistry in West Germany is Paul Crutzen.
We made the calculations and found out that a lot of ozone could be produced in the troposphere and close to the ground. And then, when we were about ready to publish the paper, as an afterthought, we started thinking about smoke, how much smoke would be produced. And we looked into that and then found that due to forest fires alone, large amounts of smoke could be produced which would block out sunlight.
This afterthought that smoke from nuclear war would have a serious effect on sunlight and climate had never been investigated by scientists, as Paul Crutzen was amazed to discover. He calculated that in a nuclear war, an area of forest the size of Scandinavia would be set on fire and produce 100 million tons of smoke. Of course, cities would burn too, as San Francisco did in 1906. In World War II, in the blitzes on London, Portsmouth and Coventry, a mixture of high explosive and fire bombs were used to devastating effect. The Allies later used similar weapons on Dresden and Hamburg, creating firestorms. Nowadays, cities and industrial areas contain large quantities of chemicals and plastics that burn with dense black smoke. This was Flixborough in 1974. Refineries and oil wells would also be hit. These might burn for months. But to know how much smoke would be produced in a war, you first have to estimate where the missiles and bombs are aimed. These are just some of the priority military targets. An analysis of them was made by Richard Turco.
In the United States, for example, there are literally hundreds of military bases, logistics centers, communication centers, and so forth that could come under attack in a nuclear exchange. It happens that many of these targets are located near cities or in cities or urbanized areas. And so it follows that in a full military attack, or what's referred to as a counter-force attack of any magnitude where many, many targets are involved, that many urban areas would come under collateral damage. By that I mean the area around the target is destroyed with the target, because the strategic nuclear weapons have such power that they can literally destroy hundreds of square kilometers of area.
Richard Turco assumed at first that about 1/3 of the nuclear arsenal was exploded, 5,000 megatons. Working with Turco, Toon and Sagan was Tom Ackerman. His task was to compute what effect the soot and dust would have on the Earth's temperature. All of them did the work in their spare time. Their computer model is known as the TAPS model, from the initials of the authors. They programmed the computer as follows. The fireballs of the largest nuclear explosions, from 1 megaton up to 20 megatons, together lift 1,000 million tons of dust high into the atmosphere. 80% reaches the stratosphere. A fifth of the explosive power was assumed to hit military and industrial targets in cities. Half of these impacts cause significant fires. 5% become firestorms, which lift the smoke high into the stratosphere. Forest fires burn an area the size of Scandinavia, raging for over 10 days. Fires at oil wells and refineries contribute 7% of the smoke and last 30 days. The TAPS computer program assumes that the smoke and dust are spread evenly worldwide and then cuts a slice through the atmosphere. The result is that 25% of the sun's energy is scattered back to space by the dust in the stratosphere. Of the remaining rays, most are absorbed by the soot. This heats the upper troposphere. Only 1% gets through to ground level, causing twilight at noon, a far more severe effect than anybody had expected.
The first figures that came out showed that the surface was getting very cold, and much colder than we had anticipated, much colder than we had found temperatures in other climate experiments that we had done. So there was a considerable sense of surprise, and I and some of the other people involved spent a good deal of time then looking at the model, trying to make sure the model was behaving properly, to make sure that we understood the reasons for why we were getting these kinds of temperatures.
The results are shown as a graph of temperature against time in days. The horizontal line is freezing point. A few days after the war, the temperature drops rapidly to 23 degrees centigrade below zero. It then recovers over the next 6 months. This graph implied the end of the natural world as we know it.
When we began our work, people thought that nuclear wars would do nothing to the climate, that their effects would be limited to the zone which was actually attacked. Our work was designed to answer the simple question, would there be a large effect on the climate and on people outside the combat zone due to a nuclear war? And these models do suggest very strongly that for a very wide range of possible nuclear wars and for a very wide range of guesses about the things we're not sure about, that there could indeed be very large effects on the atmosphere.
It became important to get some critical assessment and to encourage others to do corroboratory or conflicting calculations. We held a 5-day meeting in Cambridge, Massachusetts in April 1983. Involving almost 100 scientists, physical scientists to look at the climate effects, the nuclear winter, and a number of distinguished biologists to explore for the first time what the biological consequences were. At my urging, there was a Soviet scientist who attended that meeting.
Following the meeting, new calculations were made at the computing center of the Soviet Academy of Sciences by Vladimir Alexandrov.
The first point is that the main consequence of the nuclear conflict will be very sharp temperature drop, can take place in some days, 2, 3, 5 days. And this temperature drop will be very big. We are talking about 20, 40 or 50 degrees centigrade temperature decrease over the territory of the United States, Europe, Soviet Union. And this temperature drop will continue during many months, say 6 months or more. It depends on scenario.
Dr. Alexandrov's model used the same war scenario, but was able to compute the results in the form of a map. After 40 days, the contours show the drop in temperature. Northern Europe, minus 50 degrees centigrade. Siberia, minus 40 to minus 56 degrees centigrade. Canada, minus 30 to minus 40 degrees. The behavior of the atmosphere of the Earth is notoriously complex and unpredictable. In 1983, for example, an ocean current change called El Niño caused global weather variations. But the two computer models were predicting changes in overall climate, which is much more stable. At Boulder, Colorado, is one of the most advanced laboratories for studying weather and climate, the National Center for Atmospheric Research. In their enormous computer room are two of the largest computers in the world, Crays. Using these powerful tools and adapting existing climate models in their spare time, 3 scientists began to do their own analysis. Starley Thompson set out to check the TAPS computer results.
We were actually quite gratified to see that our results did corroborate the TAPS results. In particular, we found that the temperature drops averaged over the continents under the smoke were about 15 degrees centigrade. Now that's about half the answer that the TAPS model gives. But then again, we have oceans in our model, and the heat transport from the oceans to the land decreased the overall temperature drop for the land by about a factor of 2, and that's exactly what we found.
Their map plots the weather for each day following the war. On the 8th day, it looks like this. The blue, thicker lines show temperatures below freezing. This is for July, but already France, Germany, and southern England are below freezing point. But the effect depends on how long the smoke stays there.
Smoke is normally removed from the atmosphere by rainout, and it usually rains out on a time period from a few days to a few weeks. However, we find in our calculations that the lifetime of the smoke could be much longer. The reason for this is that the smoke in the atmosphere heats up the atmosphere and forms a very large temperature inversion. This temperature inversion stabilizes the atmosphere and suppresses the normal convective processes which cause rain. Therefore, the lifetime of the smoke will be much longer.
From another climate research unit at the University of East Anglia came more evidence that was completely independent of scenarios and computers. Michael Kelly had been searching historical weather records to analyze the effects of major volcanic eruptions. When Krakatoa exploded in 1883, it threw 4 cubic miles of dust into the atmosphere, causing dramatic sunsets around the globe. But what interested Michael Kelly were the temperature records. Did they show a temperature drop? He looked at the day-to-day temperatures following 6 major eruptions in the last century. The figures were added together and averaged to reduce the effect of weather variability, and then compared with normal years.
Surprising aspect of our results was the speed of the response of the climate system to a major volcanic eruption. Temperatures dropped by degrees centigrade, a couple of degrees Fahrenheit, within a month or so of the event. It's over the northern hemisphere land masses. We then looked in detail at the geographical patterns of temperature change and found quite a remarkable correspondence between our results and those of the Russian modeler Alexandrov. In both cases, the greatest temperature change was over the continental interiors, and in both cases, Western Europe appeared to lose the ameliorating influence of the oceans.
The temperature effects from volcanoes were, of course, far smaller, only a few degrees centigrade. Data were often missing, such as those for Central Asia. But the general global pattern is strikingly similar to the computer predictions. What's more, further evidence shows the biological effects of large eruptions. At 12,000 feet in the White Mountains in eastern California grow the oldest living things on Earth, bristlecone pine trees. The trees can live as long as 4,000 years, and within their trunks they hold evidence of the variations of the seasons for millennia. Valmore Lamarche of the University of Arizona has made a study of their annual growth rings by taking cores. When prepared and polished, the tree rings can be seen clearly under the microscope. By comparing the width of each year's growth, marked by a dark line, Lamarche has built up a precisely dated history of past seasons. But what he also found was evidence of spring and autumn frost damage caused by unusually severe temperatures. This shows up as thick lines, or even breaks in the wood. From the dated sequence, Dr. Lamarche can tell which year they occurred. The spring of 1884, just after the eruption of Krakatoa. Analysis of many samples showed that growth rings were frozen in trees growing in many locations in the same years. He then plotted the greatest volcanic eruptions against the frost damage rings. When Tambora erupted, 12,000 people died in the Dutch East Indies. The next June it snowed in New England. It was the year with no summer. Vesuvius, Avachinskaya Sopka, Krakatoa near Java, an eruption heard 2,000 miles away. Soufriere, Katmai, Agung on the island of Bali. The link-up between eruptions and frost damage showed that even a small change in climate could cause severe temperature changes locally. Mark Harwell, ecologist.
I think the example in 1983 of the El Nino event is a good case in point. Here, the average temperature decreases were probably less than 0.5 degree centigrade in the northern hemisphere, and yet the consequences were enormous throughout the world. For instance, there was extreme drought in Australia and in parts of Indonesia and southern India. And in other parts of the world, there were extreme flooding conditions, unprecedented rains in certain areas of South America and the southern part of the United States. And the winters were either extreme cold or extremely warm in various locations. So the key is that an average difference in temperature in that case of well less than 1 degree centigrade in the case of a nuclear winter, maybe 10 to 40 degrees centigrade, could have regionally and locally far greater consequences than just the average would imply.
So what difference would the nuclear winter make? These are the priority nuclear force targets and airfields in Europe. These, secondary nuclear force targets and major troop concentrations. These are only military or counter-force targets that could well be destroyed even in a limited attack. After a nuclear attack on Britain, it's estimated that somewhere between 1/4 and 2/3 of the population would survive. So what would happen to a town such as Ludlow, for instance, which looks relatively safe? Indeed, British government post-war reconstruction plans are based on the idea that areas will survive. To start with, wind directions are so variable that the population anywhere in Britain will have to shelter from radioactive fallout for at least a fortnight. And even then, the amount of radiation would be extremely hostile. The river would be polluted by fallout. The ancient castle walls, no defense against the consequences of the collapse of a highly industrialized and specialized society. No electricity. Power stations and the national grid destroyed by bombs and the electromagnetic pulse. No water, no fuel, no telephones, no banks, no manufactured products, not even soap or matches. The food shops would be empty. This is the amount of food a family of 4 eats in a year. 60 dozen eggs, 220 pounds of fruit, 370 pounds of vegetables, 540 pounds of potatoes, 200 loaves of bread, 820 pints of milk, and 520 pounds of meat. From now on, Ludlow is going to have to be self-sufficient and cope with an influx of thousands of starving refugees, many dying. It's cattle-rearing country, but any beast in the field will probably be dead from radiation. The others will soon be eaten. As for bread, if the wheat crop is reasonably dry, it will burn 17 miles from a 1 megaton fireball. Then there's the climatic change and twilight for a month. We did an experiment to find out what happens to 10-day-old barley if the light is reduced to 1% and the temperatures by 10 degrees. It's unlikely to yield any grain. On the right, normal wheat, an eared variety used for making bread. On the left, what happened when we subjected it to 3 weeks of twilight after 6 weeks normal growth. After 2 weeks of 1% light at flowering time, our experimental ears looked reasonable, but held no grain. During the ensuing famine, the climate of Britain would be changed to that of Iceland. An average of 10 degrees centigrade colder. Michael Kelly.
What this figure hides is the fact that wind directions, wind frequencies are going to be drastically altered. And on the day-to-day timescale, the timescale of the weather, we may well experience a much greater change from virtually no change at all, 2 or 3 degrees centigrade temperature drop, to possibly a 40 degrees centigrade temperature drop, depending on whether the winds are blowing off the ocean, from the pole, or out of the continental interior. And in fact, this latter case seems quite likely given the predictions of the Russian model.
The productivity of the sea depends on sunlight, whose energy is absorbed by phytoplankton, microscopic plants. On these feed the zooplankton, tiny animals, including the larvae of many larger ones. This is the beginning of a food chain. If you remove the sunlight, the whole chain collapses, even if the ocean temperature does not change much. Without the sun and the plankton, the fish would die. In any case, it would be hard to go fishing. Dr. Alexandrov.
The ocean has the tremendous thermal inertia, so the air over ocean will be cooled slightly, and the temperature decrease over continent will be very big. It will create the huge wind on the seashore, which will be accompanied by heavy snowfalls. So probably the human civilization will be erased along all seashores all over the world.
What then about America? This is a map of target areas published by the American Civil Defense Authority. It is in fact incomplete. According to them, the areas with high radiation levels are these. Of course, this official 1982 map would be very different if the wind blew from the west. But let's assume it's correct. What difference does the nuclear winter make in Nebraska, the Cornhuskers state? Central Nebraska is almost exclusively given to farming maize or corn on smallish farms. Official estimates maintain that 46% of the American population would survive a nuclear attack. The town of Grand Island sprang up around an important railway junction. The town is there to service the farms, which only produce the one crop, maize. All the supplies to the farms, fertilizer, fuel, machinery, come from very large distances by truck or rail. The immediate impact of a nuclear war would be to cut off the transport that links Grand Island to the economy of the rest of America. Electricity and communications failure would probably paralyze the town. The supermarkets would probably empty in the days of crisis leading up to the attack. Every single item in this supermarket comes from Omaha, the state capital, which is the headquarters of the Strategic Air Command and one of the most important targets in America. The average distance food travels from producer to consumer in America is 400 miles. Most fruit and vegetables are grown in Florida and California and travel an average of 1,800 miles to be eaten. It's estimated that a third of fuel refineries might survive, but 80% of the workers would be killed. Commercial trucking would stop. But it's not only trucks that need fuel. Without it, agricultural machinery is also useless. Many of the farms would still have grain stored, but it would be hard to get it to the towns. To plant the stored grain without machinery would be next to impossible. David Pimentel.
To give you an example, we presently produce corn with an input of about 10 hours per hectare of labor, of direct farm labor. If you were to raise corn by hand without this tractor power and so forth, it would require about 1,200 hours, which is 120-fold the manpower input. And in fact, in the United States, we could not produce our crops with manpower alone, even if you got everybody in the United States working on the farm to do the tillage, the cultivation, the harvesting, and so forth. We couldn't produce all this if everybody was involved in farming in the United States.
So what further problems would the darkness and cold of the nuclear winter cause? On the 8th day, in July, the temperature of Grand Island has already dropped below freezing. One night below freezing is enough to destroy many summer crops. Across the United States and Canada, at least 1 year's harvest, and possibly 2, would be lost.
My own perspective of this is that I believe that this climatic change, and therefore in turn its impact on food production, is far more important than all the radiation put together, because we cannot go more than about 2 or 3 weeks without food, and this distribution of food and so forth. So that I myself would expect far more mortality due to a shortage of food.
The Great Plains of America and Canada are the breadbasket of the world. America alone exports about half of the total grain tonnage traded worldwide. Even if the harvests could continue, world trade would cease because of the destruction of ports and the world financial system. This would have a terrible impact on the population of third world countries, many of whom are already critically dependent on food imports. The darkness and cold would not only affect the countries at war, it would sweep indiscriminately around the globe, affecting all alike with appalling extremes of weather. According to both Russian and American predictions, the cold would soon reach into the tropics, to the last refuge of natural diversity and productivity on the planet, the tropical rainforest. Two-thirds of all living species of plants and animals live within 25 degrees of the equator. The rainforest needs constant heat, humidity, and rain to support the countless, intricately balanced relationships of animal and plant, bird and insect, that adds up to the Earth's main store of genetic diversity. or more simply, the beauty and wonder of form and life. Mark Harwell.
Tropical regions in general are used to having constant physical environmental conditions. And the sorts of temperature decreases that are projected for those regions are unprecedented for them. They have not adapted to temperature fluctuations the way temperate systems may have. Therefore, I would expect they would be far more vulnerable to rapid decreases of temperature.
For this program, we subjected a rainforest abechi tree to 3 days at 4 degrees centigrade above freezing. The roots and shoot tips are injured. The structure of the cells of the leaves has collapsed. The tree dies. In the northern hemisphere, the circulating air does not normally cross to the south. So does this mean the southern hemisphere is safe? Starley Thompson.
We find that, in particular in the summertime, in the northern hemisphere summer, that the smoke cloud would not move south as a single body. What you're likely to see is that streamers of dense smoke would be torn off from the main cloud by wind shear and transported rapidly across the equator. Those dense streamers could make it into latitudes of, for example, Australia in only a few days' time, whereas the main body of the smoke cloud might take weeks. And if a streamer is sufficiently dense and large, it could drop temperatures below freezing in the southern hemisphere after only a few days.
The reason for it is not hard to understand. If you put a lot of soot and dust up in one hemisphere, then the atmosphere gets very hot because the sunlight is being intercepted by that dust and soot. The other hemisphere, at the same atmospheric pressure, there's no soot and dust, so it's cold. So in the northern hemisphere it's hot, in the southern hemisphere it's cold, the temperature difference is enormous, and so the air naturally flows from hot to cold. That's not the case if there isn't a lot of soot and dust in the atmosphere.
I would like to mention also that after the conflict, we will have very important biota-climate feedback. I mean the destruction of forests mainly. After this destruction, our planet will not have the main generator of oxygen, and the property of the land surface will be changed crucially. It means that the coefficient of reflection of the sunlight will be much higher, so the energy feed of our climatic system will be decreased strongly, so our climate could go to the new state, and this state is unknown to us.
It's no longer realistic to assume that you can merely go into your basement for a couple of weeks to avoid the worst of local fallout and then come out and resume life as it had been before the nuclear war. The simple fact of the matter is that the nuclear winter in particular that is projected and the radiation levels, the new calculations of radiation levels that are projected, mean that the world will be fundamentally changed. And nuclear war is not just a war among combatant people, but would constitute war on the environment itself.
Because their war scenario of 5,000 megatons could have such a catastrophic effect, the TAPS group were anxious to find out how small a war could affect the climate.
For example, we did a case. We studied a scenario of only 100 megatons. And just to remind you that 100 megatons is a tremendous amount of explosive power. But nevertheless, we put only 100 megatons, which is less than 1% of the current arsenals, on cities and essentially produced the same climatic effects, or if you will, the nuclear winter, as we had in our baseline case of 5,000 megatons. The reason for this was very simple. In the cities is concentrated the flammable materials that produce smoke. So with only a very small number of weapons, one can burn a very large amount of the materials that we've accumulated in our cities and produce a very large amount of smoke to produce climate effects.
Another startling conclusion challenges the credibility of a massive surprise attack or preemptive strike by one side to destroy the other's weapons. It could be suicidal, even if the other side did not fire back.
The problem with this idea is that you might be able to destroy an enemy, and you may be able to get away with it for a few days or even a few weeks. But the environmental effects would be so great, even of launching only a quarter of the world's strategic weapons, that the large-scale climatic effects would eventually come back to get the original attacker.
Conventional wisdom, no matter how deeply felt, may not be a reliable guide in an age of apocalyptic weapons. We need to do something inside our heads. We must change the way we ordinarily think about this. Einstein said after Hiroshima that everything had changed except our way of thinking. And that's the critical point, to realize that we live in a completely different world than anybody did before 1945. So simply stockpiling more and more weapons does not make you safer. In fact, after a certain point, it makes you increasingly less safe.
The Moscow-Washington Conference was about the fact that for 30 years, without realizing it, we may have been living with enough weapons to destroy the climate of our own planet. Yet it ended with cautious optimism.
On the other hand, there is also something that is very pleasing about this conference, and that is the fact that the prominent scientists who are sitting here, our colleagues, American scientists and Soviet scientists, are united in their views that there should be no nuclear war. That could only mean disaster and death for mankind. But I personally am comforted by this meeting because in our times, the authority of scientists is very great, and we should all bring our influence to bear in order to bring about an end to the arms race. There must never be a nuclear war.
In August 1984, the United States government began to set up a major new scientific study of the effects of nuclear war on the atmosphere. It will cost about $50 million over 5 years. The US government spends more than 1,000 times that figure every year on nuclear weapons.